Alrighty, I think we're gonna get started. So I'm just gonna share my screen. All right, hopefully that's up and running. Okay, so let me check the waiting room one more time. Okay, I think we're ready. All right, so today I'm just gonna do a big overview of Unit 2 for AP Physics and Mechanics. And Unit 2 is all about forces. It's all about Newton's laws. It's kind of like an extension of Unit 1. We're going deeper, we're going further. So yeah, so let's just jump right into it. We have a lot of things, a lot of topics. All right, first things first. Don't forget to check out Fiveable's social media pages, their Twitter, their Instagram, their YouTube, and this is the username. All right, let's jump right into it. All right, we have a lot of topics. So yeah, Unit 2 is a doozy. There's a lot of things. I would say the most important things are at the top here, Newton's 3 laws. We're going to go over that because that's really the heart of the unit, and the other things are definitely just as important, but they're kind of like an extension. All right, so this is kind of the game plan. But first, I'm just going to check the waiting room one more time. Okay, we're good. All right, so yeah, quick progress check. So I already did a Unit 1 stream, kinematics, all about kinematics, 1D, 2D, all that fun stuff. So definitely check out that stream. So there will be 7 streams in total. That is the plan. So we are in Unit 2. I think we're making good progress. Quick water break. Okay, we're good. So yeah, if there's like any streams that you guys want to request, if you want to do more practice problems, if you want to do more, I guess, like study kind of themed stream, just let me know. Oh, let me check the waiting room one more time. Just constantly, alrighty. Waiting room, there's a lot of buttons. All right, let's let the last people. Hello. All right, so let me just, oops, sorry, my screen isn't getting a little laggy. Hopefully you can still see my screen. Okay, there we go. All right, so let me just check the waiting room one last time. Waiting room. All right, we're good. All right, welcome. All right, so I was just talking about just a quick progress. Yeah, so the Unit 1 stream is I think already up on the YouTube account, which I believe is at Think Bible. So yeah, today we're doing a big Unit 2 review. And then, oh yeah, today is, I guess, agenda. Things we'll be going over. Newton's 3 laws, that's kind of, I would say, the heart of the unit. And then a bunch of like little extension things. They're just as important, but yeah, the big 3 are the first 3 laws, I would say. Okay. All right, quick progress track. Yes, so we have after Unit 2, Unit 3, Unit 4, Unit 5, Unit 6, Unit 7. The next unit, just as like I guess a little warning, is a doozy. I believe most people who are either self-studying or are taking the course should probably be done with Unit 2. I think, yeah, it's November, I think today's November 20th. So hopefully everyone is near this area or even further. But yeah, this is kind of a good review. So most people should be done Unit 2, I believe, in their classes. So this is a good kind of review time. All right, let's get started. All right, so before we can talk about, I guess, like Newton's laws, before we can talk about forces, yeah, this chapter, or this unit, I should say, is really, really, really heavy on forces. And I have my notes here from last year that I'm kind of referencing as we go through. So yeah, so first thing I think we should do, and this is kind of silly, well, not silly, but a little, I guess, beginner. What is a force, right? I guess at its, if we want to like just define it in its most simplest terms, I would say an interaction between two things. We can go even further and say it's like a push or a pull. Yeah, basically, I would say at its core, force is really just an interaction between two things. And here I have a bunch of forces, and we're actually, all of these forces I have on the right are, they actually have like more specific names, and that was from a couple slides ago when I talked about what topics we're going over in this stream. Those are the names of the forces that are, I have included examples on. But right now, we can just read through them. These are all forces. Right, lifting a book, right, that's a force. Our arm is kind of releasing an upward force on the book. Pulling a rope, right, that's a tension force. That is a type of tension. Skydiver falling, there is a force happening, gravitational force, like gravity, downward. Just standing on the floor is a force, and that is called a normal force. And then finally, we have a force called frictional force. Basically, when you have two things or one thing in a surface and they're sliding against each other, right? No surface is perfectly, I guess, like perfectly uniform. There's always little bridges, so there's always going to be friction, and that is a force. So wide variety. That's why I guess that's why our definition of force is so like vague, because there's so many. Everything just standing is a force, which is kind of funny. So yeah. All right, so that is a force. So those are all forces. All right, let's jump right in. So first law, Newton's first law. I would say this force is probably the most, like, I guess, well-known. Actually, no, probably the second law is a little more well-known. It's just an equation, but this one's pretty fun. I found a really fun graphic for this one. Basically, it states an object at rest will remain at rest unless acted upon by an unbalanced force. An object in motion will continue just with that constant speed and direction. It'll just stay uniform until it is, unless it's acted upon by an unbalanced force. So it's all about that unbalanced force. So I guess that's the more like verbal definition, and then we have more mathematical definition. I guess physics and mechanics is all about physics plus math. So the more mathematical definition is net force is equal to 0, means the velocity is constant. So that's like another way of saying but the unbalanced force. Yeah, when you have a balanced force, right, net force will be 0, because that let me give an example. For example, I know let me just pull this up. I can't remember if it was last stream, I introduced free body diagrams, or free body diagrams are easily the most important part of this, I guess, unit. Free body diagrams, they're whenever you have to do a word problem, we're gonna do some word problems later, but whenever we have to do a word problem, always draw a free body diagram. That's like my biggest advice. Don't be afraid to draw a picture, especially when we have some complicated pulley systems, which we'll get to later in the stream. But yeah, so that's always really, really important. So yeah, for example, let me just draw this even. Oops. All right. So for example, some people they make a mistake of saying, oh, if there's any forces acting upon it, it's not unbalanced. But I'll give you an example of when net force equals 0, but there are forces. Like let's say, let's see, I'm trying to think of this. Like I'm kicking a ball. It's going this way. I'm trying to think. The force of my foot is 5 newtons. And let's balance that out, right? We can have this. So right, so there's forces, there's obviously forces, and also had the normal force of the ground. We put some random numbers. The numbers don't really matter. I don't know, let's put 5 again, whatever. And then of course gravity. So it is, yeah. So there are definitely forces acting upon this ball or the square. Well, it's a box. There are definitely forces acting upon it, right? As highlighted by the arrows. But it's all balanced, right? So this would be a balanced. These are all balanced forces. This is a yeah, balanced forces. So just basically the main takeaway is, let me erase that for a second. The main takeaway is just don't forget that net, right? Net force equals 0. That means you have balance. If net force is not 0, right? It's a non-zero number, then yeah, we're working with an unbalanced force. So just be careful. So F net force. Okay. Oh, inertia. Yes, inertia. This is a huge vocab word that you will see when working with the Newton's first law. In fact, actually, Newton's first law is commonly referred to as the law of inertia. That's a very, very common, I guess, alternate name for it. Basically, inertia is just a fancy word for the property of objects that allows them to naturally resist changes in their states of motion. And I believe I have a fun graphic coming up that illustrates kind of what inertia is. Let me see if I can find. Oh, let me check the waiting room. I have to like. Oh yeah, and by the way, I'm also, if anyone, oops, pull that up. Alrighty, check the waiting room one more time. All right, and then for anyone who's watching this, yeah, I'm also recording this. So if anyone's watching this at home, if I'm going too fast, you can just pause it. Or if you're here and you want to ask a question, just be like, Kristen, I don't get it. That's fine too. All right, let me put this over here. All right, so yeah, I just finished talking about Newton's first law. I think it's pretty self-explanatory. Probably the one that we kind of know, more familiar with. Yeah, I would say Newton's first two laws are probably the ones that usually most people feel comfortable with, and Newton's third law is a little bit not hard, but it's just like the one that some people forget. We have the first and second laws I feel like are a little more self-explanatory. So Newton's first law, another name for it is law of inertia. And I'll explain what that means in a second. I think I have that after I explain laws. Okay, this one's cool. So Newton's, all right, so before I explain Newton's second law is like really easy. It's just an equation. But I love to figure out like relationships. Like one thing about me is that when I'm studying like physics, especially physics, where it's like a very dense subject, I always want to know like the relationships. Like why am I taking like 3 hours out of my time to learn this topic if it's like not even related? So things like that. I always want to find relationships. So I was trying to think like, is there a relationship between Newton's first and second law? And yes, there is. So basically, so the first law is very, I guess, general. Like, object at rest will stay at rest until this, or object will stay in motion at this constant thing until this happens, an unbalanced force, right? So why are we talking about Newton's second law? Well, the reason why is because Newton's second law basically predicts what will happen when a force does act on an object. So when we got that unbalanced force, right, the object's velocity will change and the object's acceleration would change, and that's where the equation comes into play. So basically, the reason why we have Newton's second law is F equals ma is basically because it tells us what happens when we have that scenario from Newton's first law, that we have that unbalanced force. Remember, net force, like having a net force that's a non-zero number is, we're dealing with unbalanced forces. Oh, and then one small thing to note, I'm going to actually draw it out right now just so we don't get confused. Technically, if we're talking about Newton's second law, remember Newton's second law is just an equation. I like to think of that. Like Newton's first law is this like, if this then that, whereas Newton's second law, it's just an equation. And really important. Yeah, it's not just, I know most people said F equals ma. Technically, it's not F equals ma because we're dealing with our net force. Because that's, reason what unbalanced forces, balanced forces, that all comes from net force. So I included the little net there. So the equation technically is net force is equal to ma. But I guess it just rolls off the tongue easier. F equals ma, but technically it's net force equals ma. Let me just double check because I think before I was talking about the free body diagram, because technically we could have forces acting on an object, but if they're balanced, then we have a net force of 0, even though there are forces acting upon them, the object. Okay, let's take a look. Oh yeah, and then usually the rule of thumb, your direction of acceleration is always going to match your direction of net force. So I think we'll see a practice problem where it proves that. But that's just a rule of thumb to make sure all the operations stay the same, because then if that's not the same, then we got to work with some negatives, and nope. Let's just, so acceleration and net force will be in the same direction, so we don't have to worry about any weird direction stuff, because that is always a problem sometimes. And then just from this equation, right, we can derive some relationships. Again, I'm huge on relationships. Right, just from this equation alone, right, we can figure out that acceleration is directly proportional to net force, right, as net force, right, if we multiply by 3, right, then acceleration will directly multiply by 3 as well. Another relationship, and remember, we're just going to compare acceleration for now. Acceleration is also inversely proportional to the object's mass. So for example, let's say, oops, sorry, let me get my marker thingy. So for example, if we're given a problem where net force stays the same, like it's locked in, and we know like the mass goes up, and to keep force to be the same, then acceleration has to go down. Or let me see if there's something else. So the first example, right, mass locked in. That makes sense, right? Mass only change, and mass is locked in. If net force goes up, just based on like math, right, then acceleration has to go up too, because it's directly proportional, just because m is locked in. So yeah, just some of these like little relationships. I know sometimes there's like multiple choice questions that ask like things like that, like directly proportional, inversely proportional, and you can use this kind of Newton's second law to kind of figure out the relationships. Oops. All right, I think hopefully Do I have the cute? Oh yes, my cute slider. Okay, so going back to just the first law for a second, I know inertia is usually like a kind of a weird, yeah, it's definitely a new term, inertia. That's not really a word we say in everyday language, like non-physics, just everyday language. We don't really say inertia. At least I don't. But another way of thinking of inertia is basically mass is an object's quantitative measure. So basically, inertia is the resistance to acceleration. So another way of thinking of it is mass is kind of like that number representing inertia. So for example, I have a stuffed bear and an elephant, right? Obviously, the elephant has a much greater mass than the stuffed animal. Therefore, its inertia is much greater as well. However, the difference between mass and inertia, they're the same thing, but mass is that it's a number that represents inertia. Inertia is not really a number, it's more like a concept, but it is the same thing as mass. Mass is just the number that represents inertia, and inertia is just a concept. So basically, all right, let me go back to this resistance. I think I was also on the first slide I wrote, inertia is the natural property of objects to resist changes, right? So for example, is it easier to push a bear or an elephant, right? It's much easier, or sorry, stuffed bear. It's much easier to like push a stuffed bear, right, to accelerate it. Whereas the elephant, its resistance to acceleration, right, it's just very heavy. So it's very hard to push it. So its inertia is high, its mass is high. That's kind of the relationship. So, all right. Oh, yes, free body diagrams. Okay, so let's talk about net force a little bit. I know I keep saying the word net force. So net force. One thing. Hold on, let me just highlight this for a second. I know I see this a lot in practice problems. Like when I was doing FRQs last year, and like I kept seeing resultant force. I was like, what is that? So I just want to, I guess, like clear this out. Net force is the same thing as resultant force. Right, result force. I think I should have realized result. Right, it's the resulting force. Right, it's the force is the result. So it is a net force. Just kind of clear that out. So if you ever see the word resultant force, that's net force. That's net force. Okay, so really quickly, I'm just gonna get rid of that. Okay, so net force. So again, forces are vectors. Just to kind of clear that out, right? When we do the free body diagrams, right, they're arrows. So they have a magnitude. They definitely have a direction. Let me see if there's anything else I want to mention. Oh, yes. So let me just go through. So yeah, objects can have forces acted upon it from different directions. Yeah, so it's not always horizontal and vertical. Sometimes you can have it like in weird, like that diagonal, like 45 degrees. This means, yeah, net force is the vector sum of all the forces. So I guess, let me just pull this up really quickly. Yeah, so when you're doing this, you always want to find the sum here. Let me get my color. I'm just going to really quickly. So we do have a couple practice problems I want to get through. So I'll just like illustrate really quickly how you would do this. So for these diagonals, oops, pull that up. So for the diagonals, obviously we want to break that up. Like if we have, let me just draw my little x-axes, y-axes. Let's say, for example, this object is accelerating. I'm just gonna pick a random. Obviously, you can figure this out. All right, set that as x. All right, just for now, just for ease, right? So how you would break up these diagonals is obviously these diagonals are not on the axes. You would have to break these up. So for example, this diagonal, the 30 newtons, 45 degrees, you would have to break that up using trig. So yeah, physics, there's a lot of, oops, right here, lots of little things, a math concept that kind of makes, so yeah, you would break this one up. And you would, oops, let me just extend that. This is what, 45 degrees, 45 degrees. So yeah, you could, for the first one, so let's say I'm gonna do the horizontal, that would be 30 cosine 45. So if I was, hold on, I'll make it neater on the bottom, I'll do the final thing. And then the horizontal, this is the horizontal, and then the vertical, this one right here, that would be 30 sine 45. So you would break that diagonal up. Because if we're accelerating, oops, let me put it over here. Yeah, so if we're accelerating, because we always want to, yeah, so again with the, I said that a couple slides ago, right? So you always want to set the acceleration equal to the direction that force, everything is kind of in the same direction, so we don't have to worry about weird like negatives. You always want to set the acceleration in the same direction as the net force. Or in other words, another way of thinking of it is we set the positive x direction in the direction we are accelerating. And yep. So if anyone has any questions, you can put it in the chat. Let me see. Yeah. So if you have a question, raised hand. Definitely go ahead.
Yes. So when you found the x and y, is that the same thing as the x and v? Is that the same thing as the x and y components?
Let's see. Yes. Yeah. Oh, yeah. Definitely. So yeah. Sorry, I should not pick H and V. That is like the worst letter. You're right. Yeah. I'll do X and Y. X component, Y component. Yep. You got it. Perfect. So just like weird terminology. Oops. X comp. Y comp. Oh, my handwriting is increasingly getting worse. Okay. I'm just yeah. So X component, Y component, horizontal and vertical. Let me see. Yeah, so so you would basically just break this up. So we don't want to deal with this right now. You broke it up into our components. And then, yeah, you do the same thing for here. And then just to save time, what you would do is to get the x, you would add up all the x. You would add this to the 25 minus whatever this was, the x component. For the y stuff, force in the direction in the y direction, you would do 20 plus this minus that 50. And then you would get your resultant force or net force. So lots of little fun names, or vector sum, however you want to call it. So really we just came up with 3 names. So if you see vector sum of all forces, if you see resultant force, if you see net force, that all means the same thing. Okay, so that is that. Sorry, let me erase that. Okay. Okay, ooh, cool. Okay, Newton's law. All right, so this one's kind of not really, I mean, they're definitely related. Yeah, all these forces are about force. All these laws are about forces, but this one is, I guess, a little different. Oops. Okay, so basically this law just says to every action, there is an equal but opposite reaction. Another way of thinking of it, equal in magnitude, opposite in direction. Fun little saying. This is always for basically saying, yeah, forces, there's action-reaction pairs, equal in magnitude, opposite in direction. And the mathematical definition is you would write it like this. Oh, and then one more thing before I move on to the next slide. Oops, move that over here. For this like notation, I always get this question because like F12 versus F21. So basically, let's say we have 2 boxes that are right against each other, right? So there's obviously going to be some clashing. Everything's being moved to the right. Right, to the right. Okay. So this is actually, oops, draw that. Okay, that's it. So let's say I'm pushing everything with, oops, I don't know why this arrow, yeah, this is not drawn scale at all. But yeah, let me just say I am pushing this big box on the left. I don't know why I keep picking 5. I'll just pick 5. I'm pushing this at 5. So this is just F. Actually, you know what? No numbers. F. There we go. Because I want to deal with just variables. So I'm pushing this. This is my hand. I am pushing the box on the left with F. So automatically we are receiving a back force, right? So this block on the right has some kind of, right? Because you can kind of visualize, like I'm pushing I'm pushing 1 box. I'm pushing, but there's like some resistance, right? And that resistance is coming from that front box, right? Inertia, right? So that box has mass, therefore it has inertia, therefore it has some kind of natural resistance to acceleration. So this force that is like bouncing back, or not bouncing back, just coming to the left, that's going to be, oh, wait, first, let me label. This is box 1, box 2. So and this is like the worst drawing. Hold on. I am not an artist by any means, as you can see from my drawing of a hand. Okay, so this force on the right is F. This force to the left, that's going to be called F12. So basically, that, I guess like the definition, or like the, what do you call it? Oh, there's a word for it. Notation is it's always the force on 1 by 2. And I know some teachers, maybe they have a different like way of writing it, but usually the convention is the first number is what the force is acting on. The second number is where the force is coming from. So the way you would read it, or the way you would like read in your heads, force on 1 by 2. So force on box 1 by force 2. Box 2. So yeah, this one on the left, maybe a different color. This is getting messy fast. Let me wait. First, erase the hand. That is the worst hand I've ever drawn. All right, the one on the left, this is F12. Sorry if that wasn't clear. Oh my gosh. Drawing with the computer, the mouse pad is hard. All right, and then F can stay. All right, next. All right, so now, oh my gosh, why is this? Okay, so there is no like left force on box 2, right? Because box 2 is just free to move, unless there's air resistance, but no air resistance yet. However, yeah, there is this big, I don't know why this arrow is so long, but then, of course, this is the box 2, box on the right is obviously being pushed, right? That's why it's moving, and that is called F21. F21. And from our rule, oops, I didn't need to circle this. Okay, there we go. By our rule, we know that F12 and F21 they should be equal, so this arrow is way too long. Again, not drawn to scale by any means. Boop, there we go. So yeah, so we know F12 and F21 are equal in magnitude due to our definition, and they're opposite in direction. So really quickly, I can explain if you're doing like trying to figure out the acceleration, right? Just from this problem alone, usually it's never 2 blocks, usually at least 3 or 4, even 5. I've had problems where it's like 5 blocks, so you just keep doing the F12, F21. F31 or F32, F23, things like that. And so when you do the net force, and so another way, okay, another notation thing, I always get this question, like, so the sum of the forces, usually you pick like a direction, X direction, Y direction, but I'll just be super general. So sum of the forces is the same thing as net force. Yeah, this is the same. So yeah, you can group this with the other like resultant force and some of the forces. Yeah, so this is all the same thing. All means the same. They're all they can all be replaced for the net force when we're doing the MA equation. So yes, when you're doing the forces in the X direction, this is really, really convenient. So let's say, oh yeah, really quickly, draw my X. Right? Always get in the habit of like drawing the axis, x-axis. So this is the direction of acceleration. Therefore, this is the positive x direction. A is going this way. We're accelerating to the right. And we know we're not accelerating the y direction because nothing is like moving, right? In the y direction. Like there is force. Yeah, really quickly. That's what I know. This is a lot of kind of going back and forth. But yeah, so there are forces in the y direction. I want to emphasize that. So even though the forces in the y direction are 0, net force is going to be 0, because right, it's not moving up and down, right? My blocks are not just magically going to the right and moving up and down. However, there are forces. There are balanced forces, but there are definitely force, right? Obviously, right, the force of gravity, so weight, and then the force of the table, because this block, or the ground or whatever. So yeah, there are definitely forces acting in the y direction, but they are balanced. So that goes back to my definition of like net force and balance stuff. So just because the net force is 0 doesn't mean there's no forces, right? There's still forces, but they're balanced, right? So net force will be equal to weight in this case. Not always, but in this case, yes. Unless we're given like the blocks are like, I don't know, being shaken up and down, I don't know. But basically, unless we were given information that the blocks are moving in the y direction, unless we're given that information, then we're good, because x direction is usually all we're given for these kinds of questions where it's like blocks. Okay. Sorry, I went on a little tangent there. Okay, so back to this. How you could work around with the Newton's third law is you can do F21 minus, oops, why is this in the way? Okay, F12 plus F equals, and then you would do M or A times N1 block 1, block 2. All right, sorry, my handwriting is, I do not have a mouse, that's the problem. Maybe if I got a mouse, it'd be easier to write. That's okay. But yeah, so the reason why this is, I guess very, oops, why is this so slow? Give me one moment, guys. Oh my gosh. Okay, whenever I draw, I notice my mouse like takes a couple seconds to like recuperate. Okay, so yeah, so automatically what's great, because this, there are, oops. Sorry, one moment. My computer is, okay, there's fine. Okay, so yeah, based on our definition, right, we can obviously use this relationship to kind of figure out like what's going on. So in this case, right, F21, let me just, oops, hold on, let me fix fix that. Negative F1, 2. So yeah, so we can basically, I got rid of the negative, just moved it over. So it looks more like this. So another way of saying that is negative F1, 2 minus F1, 2 plus F. And usually they cancel out. Maybe I set this up wrong, but usually they can cancel out easily. But yeah, so basically we can use these little relationships to kind of help us when we are given the big questions, which are things like this, when we're working with like boxes, we're working with boats, I don't know, things like that. So yeah, we can use Newton's third law to help us solve these kind of questions. So it's not like we have 3 unknowns, right? Technically, we don't have 3 unknowns, right? We have, we can use this relationship to work with things. So yeah, that was just a question I came up on the spot. I do have some pre-planned or pre-created questions. Hopefully those come out nicer. Oh, wait, first, before we do that, really quick summary. So yeah, if you are watching this on the recording, just like pause for a second. For people who are here, just read it through really quickly. Basically, everything I said. You can use all, it's kind of like, all right, really quickly. This is kind of like, what I call like little tools in our toolbox. Like these are our 3 little, like our hammer, our, I don't know, tools very well, screwdriver, our chainsaw, right? These are our little tools that we can use when we get these big word problems. These are the tools we can use. So yeah, so keep that in the back of your mind. All three laws are going to be used. I would say yeah, second law and third law are more used in word problems because they're equations and things like that. But yeah, definitely all 3 of these will be used. Oh, and then quick side note about the unit. Unit of force, right? Either just simple Newton, right? Named after Isaac Newton, or Newton's actually equal to this, kilograms times meters m over s squared, meters over second squared. And the reason why we can use what's it called? Dimensional analysis, I think is what it's called, or like unit conversion, whatever. Basically, you take the units from the equation, right? So kg is the unit of mass, and then meters over second squared is the unit for acceleration. And that's kind of how you get that. So it's like, that is definitely a question I see, like multiple choice. I see that a lot. They get like these crazy like momentum, like when we get to the momentum unit, they do a review for that. For things like that, like they'll be like, okay, so yeah, like, you know, you have like a unit, but what is another way? So in this case, like if they ask like, all right, so we know the unit for force is newtons. What is another definition? What is another unit we can use for force? And they'll have like, so they'll all be like so similar. That's the problem. They'll be like kg times like meters over second. Another choice could be like just kg. I don't know why I don't. Sometimes they throw you off. Then sometimes they'll do like Newton times second, something like that. Yeah. So obviously this would be the correct answer. If you don't know, right, go back to our definition of force. Right, net force is equal to ma. You take the units of m, kg, or kilograms. Take the units of acceleration, meter over second squared. And there you go. That's another unit for a force. So you can really work around the equation to figure out the other definitions. Alrighty, pretty easy stuff. Oh yes. Okay, I see you raised hand. Go ahead. Quick
For the
water break.
second law, when it says directly proportional, is it like proportional to the side that it's moving?
Good question. So usually, let me put this over here. So yeah, so I would say these like definitions are a little bit more theoretical. So for example, usually the applications that I would see are things like, let me actually erase that. All right, so for example, let's say you're given a question where we know mass stays the same, and then, oops, we know that mass stays the same, and basically we know that net force goes up, and then sometimes they'll ask like, what happens to A? That's all you're given. All you're given is mass stays the same, net force goes up. So then they ask like, has acceleration increased, decreased, or stay the same, or can't tell from this information. So from this information, we know for this equation to still be equal, because it's directionally proportional, and m stays the same. Really important, m stays the same, because if m's moving around, then we can't really have a conclusion. But if m stays the same, it's like locked in, and net force goes up, then we know for a fact acceleration has also gone up. I can probably bring up like more practical example of this. I have to think about it because I don't want to just like spit out a random question because I could be giving wrong information. But yeah, right now this is like for a fact. Yeah, so when M is locked. If we know that mass is unchanging, we know net force goes up, then we know for a fact that acceleration has to go up too.
This is for the question that doesn't give numbers.
Okay, yeah. So if it doesn't have numbers, oh, so you mean like, I'm trying to think.
Like more conceptual questions.
Okay, so yeah, more conceptual. So usually this relationship is more for like numbers. I've never really seen it in a conceptual way. I'm just trying to think. Yeah, like what does that mean conceptually? I'm trying to think of the best way to explain this. Because I've never really thought about it. I've just kind of like memorized it. But yeah, that is a good question. I'm just trying to think. I'm trying to think of a box. I guess all right, so the mass is unchanging. We'll just stay with that. Yeah. So yeah, all of these relationships like acceleration, directly proportional, inversely, it's always relying on one variable staying the same, unchanged, because otherwise it just can't work. So acceleration is right. So I'll go with the increasing, M has to stay the same. Yeah. So this block doesn't change mass. I'm trying to think if I can come up with a good example. Let's see, because yeah, I've always kind of just taken Isaac Newton's word for it. Let me see if there's like a good way to explain or a good way to illustrate this. So if acceleration is all right, so if acceleration is okay, all right, I think I kind of all right. So let's use a soccer ball. I'm a huge picture person. All right, so if we have a soccer ball and nothing's happening to it, it's just everything's balanced, all balanced forces, and then all of a sudden I kick it. So it's accelerating, right? It's getting faster and faster. It's accelerating this direction. And let's say now my net force has increased, meaning at first the ball was going at like 3 newtons, not too fast. But then all of a sudden it's changed to 5 newtons. All of a sudden I kick it again and like much harder. Then yeah, that would make sense. Like then the ball would kind of go quicker because I had more force. So now it's like I punched something, like I kicked something really hard. So the ball's gonna go even faster, if that makes sense. All right, that I just came up with that on the spot. I don't know if that's like, I think that's a good example. So yeah, that's a good way of thinking of it. Oh, without numbers. We'll just do like fast, even faster, even faster. Because yeah, usually these relationships like proportional and usually I like to put just substitute numbers, but even faster. Then A would increase. So as force increases, the acceleration is going to increase too, because the ball is not going to magically change mass. So this and then that supports our little like memorized, I guess, thing. F net goes up, A goes up. Did that answer your question? Sorry, I was like water break. And yeah, you can just like DM me if you have any like specific questions, because I just came up with some on the spot, so I'm not sure. But yeah, usually the questions I see like the multiple choice are like things like numbers.
That was helpful. Thank you.
Oh, perfect. Okay, cool. Yeah, actually, really, I've never really like thought about. I should probably think about what it actually means. I'm just taking Isaac Newton's word for it. Actually, I don't even know if like these are all. I should probably think about. That is, interesting. I don't know how we came upon these, but there's always a practical, I guess, application. Okay, oops. Okay, we're doing good. All right. Oh yeah, practice question. Okay, cool. Finally, so I pre-wrote this one because I knew myself, and I knew that coming up with questions on the spot is never my forte. So I pre-wrote one. Okay, so if anyone's watching this on recording, pause. Highly encourage everyone to try this on your own first, and then we can do it together. Basically, for this one, really. Actually, first, hold on. Let me just highlight some important keywords. So this is, I think I've been talking a lot, so I want to make sure everything's kind of absorbing. So, oops, why is this not working? Oh, here we go. Okay, net force, yeah. Keywords, net force, keywords, kilograms, keywords, constant velocity. Hopefully that's something I mentioned before. Okay, so I'll give a couple seconds. And I promise this one is actually, I'll just give a hint. This one, you don't have to worry about any numbers because there's a very important keyword that will save you a lot of work. Let me see if I go next slide. Okay, so hopefully you guys gave it a try or thought about it for a couple seconds. So yeah, so basically, This is kind of interesting. I came up with this question. I was like, wait a second. At first, I was actually gonna do like a numerical one. Then I was like, wait, what if I like fooled and added a constant, right? So there's two ways you could have came across this one. So again, with a toolbox kind of thing I was mentioning, like all three laws, they're like your little tools. So before you do any question, always go through each law, see like how can each apply. So in this case, Newton's third law does not apply. It just doesn't like, not really. There's no clear reaction-action pair. Like it'll be clear when you have an action-reaction pair. But this one, yeah, you definitely use first or second law. So first law, right, states, right, object will continue to move at a constant velocity unless a force acts upon it, right? We don't need a net force to keep the object moving if it's a constant velocity. I thought that was kind of like a neat. So yeah, so constant, if you're trying to keep an object moving at a constant velocity, right, there are no unbalanced forces, right? Everything's still balanced if it's constant. Constant, that's a keyword, constant. Everything is staying the same. So your net force will still be zero. So everything will be balanced. Or you can think of it like the second law, right? Constant velocity. Oh, this goes back to unit 1, kinematics, right? What is acceleration, right? Acceleration. So when we have a constant velocity, right, there is no change in velocity. Right? Acceleration, the definition of acceleration is change in velocity over time. So if we have a constant velocity, a is 0, right? Velocity is not changing, a is 0. We can use the equation, F net equals ma. If a is 0, right, then net force has to be 0, right? Because an object can't have, right, 0 mass. So oops, actually there's nothing to do with it. But yeah, so basically if acceleration is 0, net force is also 0. So yeah, net force is equal to 0. So 0 is the answer. Kind of a fun one. Hopefully, did I include a numerical question? Oh, maybe not. Oops. Okay, that's fine. I'm just here. All right. Like I said before, coming up with questions on the spot, it is not my forte. I can just come up with really quick. Oops. No. Back. Okay. Okay, but this is a quick progress check. We are almost halfway done. So again, this is a huge unit 2 review, and feel free to like, if you want to like hop off for a couple minutes and hop back in. I will be checking the waiting room. And hopefully, let me see, check the waiting room one more time. There we go. Okay, we're good. And it's like going back and forth. Okay, so I'm gonna come up with a random question. Let's see. Oh gosh, coming up with questions on the spot. Okay. Let's say we have an object of mass. Actually, well, a lot of these like numerical questions, like at least the ones that I'm just checking my notes really quickly. A lot of the like F equals ma questions, usually they're just like plug in. Yeah, so actually it's not too bad. So like F equals ma, like for example, if I say mass is equal to 2 kilograms, acceleration is 4, what is the force required, whatever, you just do 2 times 4, right? Because F equals ma, so m times a, 8 newtons. So yeah, a lot of these, actually, I think now I remember why I didn't include one, because the numerical, the more practical questions where they ask, what is the force when this is this, right? You just plug in. Sometimes they'll give you the velocities and not the acceleration. You just got to find acceleration, right? Acceleration is change in velocity or change in time. But yeah, at the heart of it, it's just plugging in, which is I think why I didn't include a question on that, which is why I included the other one. Okay, so I think the next couple slides. Oh yeah, that's actually okay. We have a good chunk, so we'll get through these kind of quickly. Okay, weight. Oh yes, mass and weight not the same. I know in like common outside of physics world language, I guess mass and weight maybe are interchangeable, but in physics, no, it's not the same. So mass is the quantitative representation of inertia, which is the numerical, right, resistance to acceleration. Whereas weight, we have gravity involved, so it's the gravitational force. And I think I have an image. Yeah, here we go. Cute little image that I found. Yeah, mass never changes no matter where we are in the universe, in the solar system. Mass never changes. Mass is just it. Like if I have a mug, and it's just like floating in space, its mass is just whatever it is. Whereas weight, right? Weight cares about gravity. And yeah, weight is measured, right? It's a I'm gonna go back for a second. Yeah, gravitational force. Weight is a gravitational force. So basically, it's a force, right? So it's measured in newtons. Whereas mass is not really a force. It's quantitative measure of inertia, therefore it's a different unit. Yeah, so mass and weight, not only are they different, like have different definitions, but they're completely different units too. Different things, different definitions, different units. So that's kind of cool. All right, next. Weight, yeah, weight is a force, meaning, oh yeah, and then we can go back to the, what's that called? Newton's second law, F equals ma, right? We can use F equals ma to calculate any type of force. So in this case, weight is a force. So these are, yeah, all of these, the next couple slides are all kind of applications of Newton's laws. So weight is a force. We can use F equals ma, where A is going to be gravitational force, or the G constant, which is 9.81 or 10. I usually use 10. On the physics exam, you can use 10. Some teachers I know my teacher, she's like, nope, no 10. You have to use 9.81. But it doesn't really matter. I mean, you're going to get the same number basically. 10 is easier to work with. But if you want to make it more accurate, you can use 9.8, 9.81, whatever you want. Whatever's your cup of tea, kind of. But usually I use 10 just to make calculations a little easier. But on the exam, you can use 10. Let's see, what else I want to say. Oh yeah, and also kind of cool. So relationships. Again, I'm really big on relationships. We can actually compare. This is the, by the way, the equation for the weight. Also, yeah, many ways you can denote it. Right, weight is equal to W. You can have F with subscript W, F subscript G, whatever you want. A lot of names for weight. I use W because it's easy to write. It's quick. W. So, oops, quick water break. Okay, I've been talking for a while. Okay, so I'm just get my water refill. Okay, there we go. All right, so yeah, so what is W? W is M times G, and we can relate. Again, this is just another indicator that weight and mass are not the same thing. In fact, weight and mass are proportional, right? Because let's say G, well, assuming that G is the same, right? G is locked in, J is the same. If gravity is the same and my mass goes up, my weight will go up too. But they are not the same. Weight and mass are not the same because of this G right here, right? Because if they're the same, it would literally just say W equals M, but no, it's W equals mg, so not the same. Yeah, units are different. But yeah, that's basically it for weight and mass. Just be careful of the wording. Sometimes questions will ask for weight. You don't forget to, if you found the mass, multiply by 9.81 and multiply by 10 real quick. Oh, okay, practice question. Okay. I believe this is, let me just double check this one. Can of paint. Okay, draw a free body diagram. My number one thing, draw a picture, understand what's going on, and then I believe, wait, hold on, quick pause. How many questions do I have? 1, 2, I have 3 more practice questions. These I pre-wrote, so I kind of thought these out. So I'll give a couple seconds. Anyone who's watching the recording, just pause it. Anyone who's here, just look at it for a couple seconds, think, and I will get the answer. I'm trying to think. Oh, let me check my notes. So you gotta draw a picture. That's always my number thing. There's so many words on here. It's just like, what's going on? Draw a picture. Especially because it's kind of like can paint. Oh, I know what a can paint looks like. Or yeah, and then hang for a rope. I know what a rope looks like. So draw a picture to figure out what's going on. I think if I go next, I will get rid of the question. I don't know. If you write down the question, pause the video. I think I'm gonna show the. Oh yeah, we've already been here 50 minutes. Oh wow, we have a lot more to go. All right, I'm gonna speed through. Okay. All right. Oh yeah. Okay, I'm just gonna get really quick. So draw a free body diagram. You're gonna draw the object of interest. What is all forces? Always draw a picture. And I think I have the solution on the next slide. Yes. Okay. So let me just draw a picture really quick. So basically, what it's saying. Let me just draw a quick little picture. It was a can of paint. Okay, so that box is my free body diagram. It was hanging from a rope, so automatically we have tension force, right? Anything rope. Whenever you see the word rope, think tension. I believe I have a slide coming up. Yeah, probably should have had that slide come before, but yeah, anytime you hear rope, tension, there's tension, right? Rope has tension, string has tension, and it goes in that way because that's the direction of the rope. Oh, and then sorry, weight. Yeah, I think those are the only. Oh, and then, yep, so tip, always set the direction of acceleration as positive, so that F equals ma will always be positive, because otherwise we're going to have some negatives. Oh, and that things get really complicated. So in this case, here, we have set A as, here, this way. I believe, wait, hold on. Let's go back first. I kind of forgot the question. What was it again? Pulled up. Oh, yeah. Pulled up. Yep. Pulled up. That's what I had in my notes. Okay, so yeah, pulled up. Accelerate up. Okay, so yeah, I have the steps listed here. So in this case, right, it's not accelerating. So in this case, I know this is kind of counterintuitive. The x direction is up and down. The y direction is this way. I mean, technically, it doesn't really matter. You can just set this is y and this is x, but basically, there are no, oops, there is a net force in this direction that I've put horizontal line there, it's 0. So everything is vertically, so you would do T minus W equals MA. And then we are using our definitional weight, right? This is where, again, our toolbox of tools, right? So we really just want to find this answer. So T equals W plus MA. W is mg. We can take m out. We have g, well, that's 10. We have a, I think I gave the number as 1, and ta-da, we found our tension force, and that was the question I was looking for. Oh yeah, go ahead, questions.
Isn't gravity equal to acceleration?
So why good question. That's a good question. Yeah, so in this case, what's it called? Acceleration. I think okay, so in this case, acceleration is up. Let me go back to the question. So in this case, the A that I'm referring to is the acceleration that we are pulling the rope up. So in this case, let me go so in this case, acceleration, we are not solving for the acceleration due to gravity. We are solving for the acceleration, different acceleration of the thing going up. Let me see if there's anything else I want to mention. Yeah, so I think that's the biggest thing. So we're not solving for the acceleration due to gravity. We're solving for the acceleration that we are making. Basically, we are causing that our arm is causing the acceleration. It's being pulled up, and that is upwards. So it's not due to gravity. However, gravity is definitely acting on this canopate, and that is represented by this 10. So actually, gravity, I know this is, oops, go back for a second. I know it's kind of, the whole concept of gravity is a little bit weird, but gravity is a force, right? It's the downwards force. However, let me close over here for a second. Gravity technically, right? Because I know when we write it, it's 10 meters per second. So, so gravity. Oh yeah, sorry. Weight is a force. Gravity is usually considered like a constant. And I know we always say acceleration due to gravity because the unit is the same unit as like acceleration. So in this case, I lost my train of thought. What was I gonna say? It's me circling. Yeah, that's basically it. So it's acceleration, it's different. Gravity's definitely acting upon this canopate, and that's why it's G plus A. But yeah, this A has nothing to do with gravity. This A is man-made. We are pulling it up. That makes sense.
Okay, and the G is positive because it's going up?
Yeah, good question. So let me put this over here. So that's a great question. So G, I know usually in this case, right, G would be gravity is acting down. However, G is a constant. Yeah, that's kind of what that's what I was trying to say before. So G is a constant. So in this case, let me see if I have, so in this case, you would not put like negative G or anything like that. In this case, we treat G as a constant. I'm trying to think of a time when we would use negative. I'm trying to think of a time. No, yeah, actually, in this case, I think all cases, G is a constant. Hold on, I'm trying to think of the time. I've definitely dealt with, because negatives and positives, signs are always when things get weird. It would always be positive. The only time it would be negative is if we had things like negative mg In that case, it would be whatever mass is times 10, and then we would have a negative number. And the negative would be because of the algebra, we're moving things around. But yeah, so G is, I know that's a good question, because G in this case, gravity, yeah, it is downwards, and that would be negative because we've set up as positive. So yeah, I would just keep in the back of my mind, G in our equation is a constant. It's 10.
Wait, so I'm still a little confused because G is like when G is going downwards, it's positive, right?
Yeah.
But in this case, isn't it going upwards?
That's a good question. Hold on, I'm just gonna really quickly check my notes. Put that over here because I'm trying to think. Yeah, so if we set G as negative, like let's say G was negative. Hold on, let me check my notes for one moment. Yeah, I would yeah. So in this case, gravity. Oh, you know what? Okay, I figured it out. So the positive, negative, the weird signs, right? Those are all applicable to forces, and G is not a force. So I know gravity, weight is a force. Weight is a force. So it definitely follows the rules of positive and negative. So in this case, it would be negative, right? This comes from here. But G is not a force. So therefore, it doesn't follow the sign, the positive, the negative. G is it's technically a type of acceleration, because remember, G, the unit is, like if someone asked, what is G? You would say G is equal to 10 meters per second squared. So I guess you can define it as an acceleration. And that's like a weird term. Gravity is an acceleration. I remember having this debate in my class last year, like, is gravity a force? Is gravity acceleration? In this sense, in all like cases moving forward, gravity is not treated the same as like a force. So it's not like W, it's not like T, it's not like normal force. It's G, because G, we would never write G is equal to 10 newtons, right? It's not a force. So it doesn't follow the signs. Therefore, G is always 10. Even if up is negative, down is positive, or up is positive, down is negative, G is just always 10. Always 10. It's never negative 10. It's always just 10. It's a constant. It never changes. It's always 10. Whereas W, it can change depending on the mass of the can of paint in this case. So I would just like write that down. G is always 10. Because gravity, I guess in its most simple sense, is an acceleration, not a force. Weight is a force. Weight is mg. Weight is a force. Weight follows the weird signs, right? If up is positive, and weight will be negative. If it's accelerating downwards, weight is then positive. But G is always just gonna be 10 because G is a constant. That's a good question though. I never really sat down and like thought about that. But yeah, G is a constant. So whenever you see G, just plug in a 10. Or 9.8. Or 9.81. All right, hopefully that answered your question. Let me just see where we're at.
Thank you.
Yep, no problem. These are great questions. I never really thought of these. You guys are like good with these questions. All right, let me clear that. Yeah, I never really thought. I just kind of, oops. All right, cool. So that is that. All right, so really quick, we're just gonna speed through these because I have 2 more questions that I want to do, and I don't want to have the stream be like, it's already an hour long. So I think it's fun. I don't know, physics is fun. I could talk about this. I love like even the things I don't know. I'm just like, there's probably some kind of law or some kind of rule. I can probably figure it out, you know. So I don't know, physics is cool. Okay, what is this? Oh, normal force. Okay, so normal force, it's always perpendicular to the surface. It's basically, I think normal force is the most interesting. It's literally just the thing that is stopping an object from just falling through. Like, for example, the table is exerting a normal force on my mug. If it wasn't for the table, my mug would fall right to the floor. And me, normal force is exerting force on me. If it wasn't for that normal force, I would fall right through the chair. Yeah, so normal force is N, or it's Fn, always perpendicular to the surface. It goes straight up. Like, for example, small thing. If our surface is like that, horizontal, then our normal force will go like that on the box. However, if our surface is slanted, and I believe I have a section on inclined planes, then the normal force, still remember, perpendicular 90 degrees, our normal force is going to look like this. It's no longer straight up because then it's not 90 degrees to the surface. So basically, the way I like to think of it is basically a thing that is preventing an object from just like falling straight through. So it's just support, the support force, I guess you could call it super casually. It's not actually called the support force, but it's another way of thinking of it. So, all right, after normal force, we got friction again, pretty self-explanatory. Whenever you have two rough surfaces or one object with the surface and the problem says we got a surface with friction, we're dealing with another force, friction. How that affects our free body diagram. Again, I just want to go back to like our word problems. If you have a free body diagram, right, we got normal force and we got the weight. Those are equal. They're balanced, meaning there's no acceleration in the y direction. Net force in the y direction is 0. But we kick the ball, it's moving the force on my leg, but the grass has friction. This is how it affects. Ta-da, we have a lowercase f. So now we are dealing with forces. Let's say friction force and the force that I kicked the ball with my foot, they're not equal. We got we're dealing with an unbalanced force. So in this case, force in the x direction is equal to force that I kicked the ball minus that friction. And we'll define what friction is in 1 second. But yeah, that's how it changes our equation. We have to include the minus f. So, and to find f, it's kind of fun. We'll see. And let me just erase that. To find f, it's an interesting kind of journey. So, however, there's two types of frictions. There's static friction, kinetic. So static is kind of like what I like to think of. It's like we're on the brink of moving. Like I'm pushing this box and it's not moving yet. The box is not moving. It's like right at the point. It's breaking point. Like it's just about to move. And static friction is always greater than kinetic. And I have a slide on that in a second. Kinetic is we're moving. I'm moving the box, and there's this constant friction force against the box as I'm moving it. So kinetic, moving, static, not moving yet, but it's about to move. It's on the brink of moving. Oops. Here we go. So yeah, static. I have an example. That resistance you feel when you're pushing a really heavy box, we're feeling some static friction there. Kinetic friction, we're pushing and we're experiencing resistance as you're sliding it. That's kinetic friction. Okay, and then strength. Yeah, so how strong a friction force is depends on two things. The type of surface and how strong the normal force is. So there's where normal force comes in again. And there's actually an equation for it, which I highly encourage memorizing, but there's a fun way to memorize it. Type of surface. Okay, so type of surface, how rough it is. It plays a huge role in the strength of the friction. So in this case, right, ice. And this symbol, by the way, is called mu. It's kind of like a U, but like with it's like a Greek letter. It has like a little line on the left side. It's called mu. Mu is the coefficient of friction. Basically, the higher mu is, the stronger the friction force. So for example, ice, right? There's like no friction there. It's very smooth. It's just the way ice is. The mu between my shoes and ice is really, really small. Whereas if I'm trying to walk across like rubber, oh boy, I would have trouble. Like I might like slip or something. The friction force is really, really high, meaning that mu is basically just a representation of how rough the surface is. So mu between my shoes and rubber is really, 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 really high. Just trying to think of like another what else is good? I guess like a rug kind of has some friction. Like if you're wearing like rubber shoe, yeah, I can just imagine like tripping over that. Maybe a polished wood floor, like where it's no little holes or anything, no little ridges. That could probably have a small mu. But yeah, so and then let's see where this all comes into play. Some equations, yay! So there are two different coefficients. I know we talk about mu, but there's mu k and mu s. So this mu k is for kinetic friction, and then this mu s is for static. And this is like a little equation, or not equation, just like inequality that you can try to memorize. Static mu or static friction is much greater than, or not much, but it's greater than kinetic, right? And it makes sense, right? I'm just trying to think like practically, right? It's much easier to keep an object sliding once it's sliding, kind of like Newton's first law, right? It's easier to just keep things going. Whereas if a thing is like just stuck and I'm starting to push it, right? Its tendency is to just stay where it is, right? So the box is like, don't move me. No, not really. The box doesn't talk, but you know what I mean. So just think of like a really heavy box. Like when you're just trying to get it to move, is much you have to much more force, and the mu is much higher. Whereas we're just moving something that's already moving, it's not as bad. It's kind of easy. And then here's the equation. So this is how we find friction. So there's two ways to write it. You can do F friction or just lowercase f. A fun little way to remember it is physics is fun, right? So F equals mu n. I know some people are like normal force. What does that have to do with friction force? Well, this is where it has to do with it. So let me see. All right, so yeah. And then three more equations to kind of remember. Just remember static friction. Yeah, so where is it? Kinetic friction is the easiest. It's just Fk is equal to mu k times n. But static friction has two. And the reason why is because, again, static friction is kind of tough. Because let's say I'm pushing a box, but I'm not at that breaking point. I'm not at that breaking point. I'm like pushing kind of lightly. I guess I'm still experiencing, the box is still experiencing static friction, but it's not experiencing its maximum static friction. I'm just pushing lightly. I'm definitely experiencing a force, the friction, but it's not the maximum. So it's going to be less than or equal to its maximum, and the maximum is equal to. That is right when it starts to move, like right when, like it's like on the brink of moving. That is your maximum static friction. That is the most that box can take, and then our force overtakes the static friction. So I think it's a good kind of fun way to think of it. Alrighty. Oh, I love this one. All right, this is like unrelated to the exam, but I thought it was really interesting. Actually, this has to do with the unit of rotation when we get to that unit. I think it's unit 5, or I forget the number, but yeah, this has to do with the rotation. But really quickly, static friction. I know some people think, oh, static friction, not moving. And I know I said that before. However, I will give you one example. A ball rolling technically has static friction. And I had this drawn. I couldn't find it online, but I can draw it for you. Basically, when you think about it, right? I know this is a very, very weird, I guess, example to think of, but basically we have this ball, and you can kind of think of it as there's like little feet. I know this is really weird, but I think this is the best way I can explain it. Little feet on the ball. So basically, when a ball is rolling, right, that surface, like it's like a new surface touching the floor at every single second. So basically, and this is like the worst drawing. This is like really disturbing. Like, there was like an actual picture of like a ball with feet, and this is much better. If you saw that drawing, I think it would click a little bit more. I wish I could draw feet better, but basically, every time a new surface of the ball hits the floor, it's technically experiencing static friction because it's touching for like a little bit, and then the ball continues rolling, and then a new surface touches, and so it's a kinetic would be a block, same surface against one surface, and it's moving. Whereas static friction is basically, in this case, it would be a new surface is touching each one. So it wouldn't be kinetic because nothing is sliding, right? Because kinetic, there's no side of the circle is going to rub against the floor. A new surface of the ball is going to rub against the floor at every single second. So it's actually more like each little like square centimeter of the ball that's rolling against the floor is like a foot, and each one of them is experiencing static friction as the ball is rolling. So it's not like kinetic friction would be this ball is sliding and maintaining its like orientation, if that makes sense. This is not an exam, so you don't have to memorize this or anything, but I just thought it was kind of fun to kind of visualize. But yeah, so if you have any questions, just let me know. It's a fun little example. Okay, let's speed through. Ooh, we're almost done. Okay, so this is our third question. We have, I think, this one and then one more that I kind of pre-wrote, because again, I cannot come up with questions So I'll leave a couple seconds to read this one, and then I will kind of go through it. So we're given mass, we're given coefficient mu s, we're given a force, we're given the direction, and will the box slide? That is our question. So basically, will the force overcome the static friction? Okay, let's move to the next slide. All right, so yeah, first things first, draw a free body diagram. I cannot emphasize this enough. Go straight to the question. So for this one, again, draw a free body diagram. Answer is the body. Oops, the box will not slide, but I will still kind of illustrate it. Oops, I don't even remember the question. Hold on. Probably should have wrote this down. Let's see, what was the box? System floor, coefficient, force. Okay, so right off the bat, right, we have a force and we have a friction force. Okay, and of course, there's a normal and weight that's balanced, and this is what this is balanced. Everything on the y direction is balanced, but it's moving. This is lowercase f. Okay, so we're basically asking, is the force that's being exerted, is it will it overtake static? Let me just double check on that. Force is, yeah, is it going to overtake it? Okay, so first thing we have to do is find that static or max static friction. So we can find n right through the net force in the y direction. That's equal to 0. So we can do n equals mg. Right? We can set n equal to w. That's fine. Because let me just illustrate that a little bit clearer. Fy is equal to n minus w equals 0, right? So then n equals w. That's how we got that. So yep, n equals w, n equals mg. We got 1,000. Plug that in. We were given 0.4. All right, so we got it. Our maximum static friction force is 400. 400 is the maximum. But, right, we are only pushing this at 250, meaning that static friction force is strong, meaning our arms are not big enough. I mean, our arms are not pushing enough, so the box is not going to slide. So that's kind of how you would solve that. Clear all triangles. I think that one was a fun little one. All right, we're almost there. We're almost there. All right, 3 more topics, and then we're done. I know we've been here for a while, so yes, go ahead. Question. Water break.
Wait, so how do you know that the box will not move?
Good
So
question. All right, sorry,
the max static friction is 400 newtons, and then the force that's applied is 250. So like, is the max static supposed to be less than the force that's applied?
Yeah, good question. So I like to think of this like I'm acting like I'm physically pushing a box. So you can kind of think of it like I'm pushing only 250. Let me erase that. So yeah, I'm only pushing at 250.
You don't have to draw it out. You can just.
Okay, yeah, so okay, that's fine. So yeah, basically, if I'm pushing at 250, and then the friction force is 400, that's the maximum. And yeah, so that's a good question. Yeah, so if what's it called? So in this case, yeah, we only care about the maximum. I'm trying to think like, because yeah, the static friction is like actually no, because it would be 400. Yeah, so the maximum and the whatever. So usually when we talk about F static, it's always going to be, we're talking about the maximum, because that is essentially what static friction is. Because technically, I know the definition before was like if it's less than or equal to. I mean, we could like take advantage of that and be like, oh yeah, static friction is 1, like if I'm only pushing a little bit. So whenever we talk about static friction, we're talking about the maximum, because that is truly in its essence what the static friction is. So just on its own, the static friction is 400. That's really, really strong, meaning, static friction always goes in the opposite direction of the force that is supposed to accelerate. So we are trying to accelerate it. We're trying to push we're pushing 250. We're pushing 250. But that friction force is so strong. It's 400. So that resistance force, right, that the box is experiencing the opposite direction of us pushing is really, really strong. So 400 newtons to the left, or not to the left. Oh yeah, it is facing to the left, but it's not moving to the left because it's static friction. It's not like a moving force. And then we are pushing 250 to the right. Nothing is moving because my 250 has not overtaken the 400. If that makes sense. That's better wording. So it's kind of like a numbers game. Like who's bigger? 400 is obviously bigger, so that 400 wins. My 250 was not enough to move it. Because if to get the box to start moving, I would have to get at least 400 newtons. Because then I have officially overtaken the static friction. If I am really strong and I can move the box at 450 newtons, that is greater than the static friction. Therefore, the net force in the x direction would be going in my direction, the way that I'm pushing. Static friction does not move to the left. Like, so I think the best way to draw is like the free body diagram. If I am pushing to the right, only 200, a little tiny number, but then the static friction is all the way this way. This time it's drawn to scale, like 400. Basically, oops. Oh yeah, awesome. Thank you. I can go on a tangent. It's bad. I'm sorry. All right, cool. So yeah, so I haven't overtaken that static. However, important note: static friction doesn't really, it doesn't move. Like the box is not, the box is not like anti-accelerating. It's not like moving back. It's like, whoa, static friction is so strong, I'm moving back. No, it doesn't really do that. But it is a very strong force in this case. Not always, but. Alrighty. Oops. All right, we're almost there. Pulleys. Yeah, pulleys are weird. I'm gonna be honest. But usually in these kind of questions, they're frictionless, they're massless, because we want to focus more on the object's interest, like the box. We always blocks. Those are usually the ones they ask us to figure out. What's the acceleration? What's this? What's that? Tension force. That's usually the ones they ask for. And I believe, what is this? Is this a practice problem? Oh, it is. Okay. Find the acceleration of blocks after they are to two. All right. So before you do anything, draw a free body. I think that's like the takeaway for today. Always draw free body diagrams, no matter what. So the first thing I would do is I would look at the image, I would digest it. All right, I know for a fact if I had these two blocks, I let go, it's going down, right? It would accelerate in this direction, right? This block would go this way, this block would go down. Like I can visualize that, but that's all I can visualize. Now it's time for body diagrams. So let me just show the answer. Yeah, we have two blocks. Yeah, we're working with two free body diagrams. Let me just draw. I think the first one was like this on the table. The second one was hanging off. So always set the positive x direction as the direction of acceleration. The second block is accelerating downwards. This block is accelerating to the right because it's moving to the right. So A is this way. X direction is this way. Positive x, sorry. Oh, that looks like it's saying plus x. No, positive x. Okay. Right, and then Newton's second law. This is where Newton's second law comes into play. We want to find the acceleration of each block. So the block on the table, let's do that one first. Basically, oh, this is where the rope was. Right, there you go. So on the table, right, balance forces on the y. So we're working with only one direction. There's no friction. I think it said frictionless. So no friction, thank goodness. So that means T1 is the only force in the x direction. It's going to be equal to ma. I have these little subscripts just to specify because this is box 1, this is box 2. You don't want to mess up which one we're working with. Hanging block, weight is positive. Tension, right, that's the rope we're attached to, minus tension equals ma. We have two unknowns. So basically, we can add these equations together. So we get T plus, oh yeah, and because it's the same rope, you can, what's it called? You can, what do you call it? Eliminate it. So, but if we had like a thing here, like if I had another block here, that does not work anymore because now it's two different ropes, kind of. I know it's weird, but if we're working with one rope, it is all the same tension. So eventually we get equals A, I'm just going to do this, M1 plus M2, right, T minus T, that's 0, boom, boom. So we get W, which is, oops, M2G is equal to A, M1, oh my gosh, why is this so slow? M1, M2, hopefully my handwriting's getting, oh yeah, sorry, any questions? Sorry, yeah, go ahead, sorry.
So two questions. One is, what does W and T stand for? And two is, you could just like say what they mean. And then two is, Oh yeah, the masses weren't told, right? Like they weren't given.
Yes, good question. Masses were definitely not given.
So,
So yes, go ahead, sorry.
how would you calculate that?
Mm. In this question, yeah, there is no numbers, so that's kind of a fun one. So yeah, there's no numbers involved. So yeah, this is actually the answer at the end, which has been bolded. This is the answer. So you cannot solve for a number. Just you're sometimes good, sometimes bad. Some people like to see a number, but yeah, this one there is no numbers. This is the answer. And tension is, or sorry, T is tension, which is every time you see a rope, there's tension involved. Basically, tension force is that kind of force that comes along with like anything that's stretchy, like ropes, like strings. Trying to think anything else. Yeah, usually that's the only two. Yes, strings and ropes are like the biggest things. Anything that's like stretchy. And then what was the other one? Oh yeah, W is that's weight. So yeah, weight again. There's like a lot of ways you can write it. W is the same thing as mg, which is the same thing as some people write it Fw. Some people write it, but yeah, it's just that that force it goes down. Hopefully that answered. Oops, clear that. Okay, cool. So I think, hold on, quick progress check. Oh, we're almost there. Okay, cool. All right, inclined plane. Yeah, this is the easy stuff. All right, so inclined plane is literally just a ramp. However, whenever you get an inclined plane, you can't do this anymore. We can't do our normal x, y, because oh boy, then we would have some crazy numbers to deal with, because then we have the arrows everywhere. I don't want to deal with arrows. So instead, let's just set x to be parallel to the incline, set y to be perpendicular. Therefore, automatically, acceleration in the y direction will be 0, right? Because the block is not magically just going up and down. The block is always just going to stay on this axis right here, right? The block will move here, then it'll move here, then here. It'll never just magically pop up there. So we can eliminate some stress by setting this as our new direction. However, the one problem is weight, right? Weight is always just vertically down, but that's okay. I mean, I'd rather deal with just one that's like different than the rest. Like normal force would go this. Normal force would go this way. You would separate this W, the weight force, into components. So Y component is like that. X component is this way. If you had friction, it would go this way. So I think along an axis, which is nice. But yeah, weight would be the only one that's like a little weird, but that's okay because we can set it up to Y component, X component, using the sign. Oh, and then this would be the new theta, because right triangles, again, trig, it's all related. So this would be 90, this would be 90, or like this would be the not theta, and then this would be, hold on, let me draw this a little better. There we go. So yeah, this would be, what is it, 90, 100, yeah, so this would be the not theta, and then this would be the theta, if that makes sense. I'll explain that better later, but that is just for the sake of time. I don't want this stream to go like, so I'll just pause that for now. I can explain it in another theme why that is theta, but there is a reason using the right triangles. Okay, we're almost there. We're in the home stretch. I have 4 more slides on uniform circular motion, and then we are done. If you have any other questions, just like if anyone was watching the recording or is here, feel free to just message me on Slack. All right, so yeah, these slides were actually taken from my other, on my Notion. I do have a Notion Physics Team Mechanics Hub Notion page, which is like, I have a bunch of slides on there, a bunch of resources that you can check out. I just took this from these slides because I already made a slideshow on uniform circular motion. I just took the first 4 slides. So I'll go with super quick, but uniform circular motion is, I think, a pretty easy. I think I mentioned it last stream. I can't remember. But yeah, basically, uniform circular motion in a circle. Constant speed, direction is always changing. Therefore, if velocity is changing, there has to be some kind of acceleration, because that's the definition of acceleration, right? When velocity is changing. I know speed's not changing because it's uniform speed, but however, the direction is constantly changing. And velocity, right, is not just speed, but it's also direction. So now the question I ask ourselves is, where is that acceleration coming from? And the answer is, ta-da, oops. Yes, there we go, centripetal acceleration, however you want to pronounce it. Centripetal, same thing. But yeah, here's a cool graphic from Physics Ninja. I thought this was a great little graphic that kind of explains it, right? Velocity is always changing. I mean, the magnitude of velocity stays the same because it's uniform. However, the direction is constantly changing. So what is causing that change? It's because of the centripetal acceleration. It always points to the center of the circle from any point on the circumference of the circle. And this is what it equals. Something you kind of memorize. I'm pretty sure it's on the reference sheet, because if you're taking the Physics C exam, there's always gonna be a reference sheet, and I'm pretty sure it's on there. If it's not, it's an easy one to remember. Centripetal acceleration is equal to v squared over r, where r is the radius of the circle, a constant, and v squared is the tangential speed, which is this speed that's a tangent to the circle. That's also a constant. So centripetal acceleration is always going to be the same no matter where you are in the circle, which is kind of cool. Oops. All right. So now you're wondering, where does that centripetal acceleration comes from? This is where Newton's laws come. I think this is where I stopped during the first stream. This is where I'm going to resume. So centripetal force is the reason. And then this is kind of cool. So we know that centripetal acceleration is equal to v squared of r. So now we have to find centripetal force. We can use the F equals ma, right? So centripetal force is equal to m times this. So mv squared over r. So that's where it comes from. Some people just memorize, oh yeah, centripetal force, mv squared over r. Where does that come from? Some people don't know, but it actually comes from the Newton's second law. So everything's kind of connected, right? Centripetal force is a force. Therefore, if it's a force, it can follow the m equals ma equation, which is helpful. So everything's connected. Okay, what is this? Oh yeah, how do we calculate? Use Newton's second law. There you go. That's a nice little graphic. I have a bunch of little graphics here. What is this? Newton's second law. Quick sneak peek of how. Oh yeah, rotational. I'm gonna skip that for now. And yeah, all right, we did it. An hour and a half. Huge review. This was definitely an overview. I wouldn't even call it like a. I mean, it's a pretty comprehensive review. I think I went over most of the things. There's probably like little topics here and there, but I can definitely do a shorter stream in the future where I just do practice problems, or we just do like multiple choice questions, or we just do FRQs. This was just a good review, a good starting point. Hopefully the 4 questions that I picked out were okay. But yeah, thank you all for watching. Thank you for coming. If anyone's watching this recording, thank you for watching. Hope you learned something new. Hope you reviewed something that was important. I'm always here for questions. I'm always here if you have a question. I'm here to give you answers. Work around, like, even if I don't know the answer, I will work on it with you. That's the magic of physics. There's always, if there's a weird equation or some kind of weird phenomenon, right? There's probably some law or some equation that we can probably use to figure it out. That's one of the reasons why I like physics so much. Like, it's dense stuff. It's very dense, but it's fun. At the end of the day, it's fun. Yeah, awesome. Thank you. Let me stop sharing for a second.
This was helpful. Thank you so much.
Yeah, this was fun. Thank you so much for coming. All right, so let me just close this. All right, so I'm gonna stop the recording.